Hey PChem class, I said I would promise to make you a short video on a piece of Wednesday's class that I know probably came at you a little heavy, but maybe this narrated video will help you a little bit and give me an opportunity to highlight the piece or pieces that show up later that I really would like for you to understand. So what I'm walking you through is a bit of Chapter 2. Specifically, let's see what I got here, about pages 36 to 39. This is a transition between the kinds of things you learned about in Gen Chem and what we try to do in physical chemistry. I'm spending a lot of time just on these couple of pages, not that we'll do it every single time throughout the semester, but to demonstrate what PChem really does. It takes things that we observe that can be understood in a this phenomenological, I keep using this word, or macroscopic way, the things that we can see at our scale, and reduce them to or connect them to the kinds of things that we can calculate about individual molecules. So I just sort of summarized the opening page of this by describing this in detail, as you could read. This idea about a more satisfying model is really what science is all about, is trying to understand the underlying reasons for seeing what we see. Now, you may have thought some of those van der Waals equation problems or the virial equation problems were challenging because you had to be really careful with units and all that. And it might have given the impression that those equations were explaining what's happening because it did account for real gases. If you recall, in van der Waals in particular, we said that there was a term that was correcting for the attractions between molecules, and then there was another term that was correcting for the size of the individual atoms. Well, the fact was, it did indeed correct for those terms, but it did it in what's called in science an empirical way. Basically, those values, A and B, which are kind of like the little adjustments or fudge factors in the equation, they were developed using measurements. If you remember, you have to find the critical constants when the material turns into a supercritical fluid. So in a way, you were helping explain real life by making measurements of real life. It still wasn't the theoretical underlying reasons for the macroscopic behavior being tied to molecular motions. So that's what we're going to try to do now. So let's revisit this idea of a sample of gas. And the book says you have a cubic box. You don't have to have a box. You could have a balloon, of course, or something that contains gases. But in this case, it's a box of identical atoms bouncing around inside the box at some temperature. It doesn't really matter what it is. We're going to focus on the motion of just one of those molecules, which is illustrated here with the red. So the vector that you see starting at the origin and going out to this dot is representing the velocity of that molecule, or I should say atom, flying around inside the box. Of course, there are many, many molecules inside the box, but we're just going to focus on one and try to break it down into its components. What this does is it takes this velocity, which of course we mentioned in class has a particular direction, and it resolves the motion into components along the x, y, and z coordinate system. So for example, what you see here, this projection of the dot down to the xy plane, shows that you can get the x component of velocity by doing that. The y component of velocity is going to go out to here, and then there's going to be a z component of velocity. And of course, there's going to be a relationship between each of those individual components of velocity and the whole. And so basically, equation 2.1 describes that for you. The relationship is it uses essentially Pythagorean theorem, and it says that the individual components, whoops, got to do an eraser there, the individual components squared, all taken as a sum, are equivalent to the velocity vector squared. So this is saying, again, I'll just write this out, the square of the velocity of an individual molecule is the sum of the squares of the directional components. Okay, now let's kind of keep that in check and go back to a little bit of what we learned regarding force. So let's kind of number that sort of piece one, and we'll come back to it. Piece two of trying to understand individual molecules' connection to macroscopic identities is to think about the definition of pressure. And we did this earlier in the semester. Basically, force over area. If you remember, force can be represented in physics class as mass times acceleration. So force is equal to mass times acceleration. And a little bit of derivation hopefully can remind you that acceleration was equal to velocity, or the change in velocity over time, or velocity over time. That can be rewritten as distance over time squared. Okay, so acceleration can be force can be rewritten as mass times distance times time to the minus 2. I could have put over time squared. Here, the definition of momentum comes into play. Momentum, if you recall, is mass times velocity. So, I could rewrite my expression for force as momentum over time, using the definitions we mentioned earlier. Okay? So this ends up being a key finding. The force of a collision is going to be its momentum over time. How many different transfers of momentum there are in a particular unit. Let's see, I don't think I have enough room here. Momentum over time. Okay, so if we make as simple as an example as possible, the collision of the wall, the collision of the particle with the wall is going to result in a change in momentum. What was moving to the right, and since I'm going to make this imaginary molecule, not imaginary molecule, but I'm going to say the molecule has just complete directionality in the x direction, the momentum after the collision is going to be this value. And since there's conservation of momentum, the change in momentum of the particle has to be exactly equal to essentially the momentum absorbed, if you want to think of it that way, by the wall. Okay? And so this gives us a clue to where we're going when we wanted to connect this to force. So again, if pressure is going to be related to the force of a collision, and the wall is absorbing that force, then we could sort of rewrite conceptually what we have above circled as to the change in momentum of the particle. Change in momentum of the particle, and essentially multiply that times the frequency. So for every collision that occurs, I'm just drawing these arrows to represent 5 different collisions. So you can imagine this thing bouncing back and forth like a ping pong ball. And let's say in some amount of time there were 5 collisions. How much force did the wall absorb? Well, it would be, in that case, it would be 5 times 2m vx, because that's the change moment of each collision, over the time that we did this, or the frequency. How many per time? In case you need some clarification on what I mean by frequency here, there's so many different ways to think about it. You could, in a few pages, we're going to be talking about diffusion and effusion, and you could even think of the word rate to somehow be related to frequency. The whole point of that is kind of collectively, it's an idea that has time in the inverse, and we use it in many different ways in chemistry. When we talk about light, E equals h nu, you might remember that the frequency of light, it talks about how many cycles per second. Again, time is in the denominator. When we talk about the rate that molecules, let's say, would hit a hole for effusion, which is gas molecules leaving a pinhole, you talk about an amount per time. You could use the word rate or frequency in both of those conditions. My main take-home message from this slide is to get across the idea that the force of a collision, or many collisions, is going to basically have a momentum term. For us, it's a change momentum times a rate term or a frequency. That's going to lead to force. Now, once you have an expression for force, you know that you can get to pressure. So let's be more explicit with how we're going to get an expression for force in our example. Well, this goes back again to my imaginary perfect collision that's just in the x direction. I think I mentioned this one in class. If you think about how often the particle is going to come back and hit that wall again, you have to think about the time it takes to make a trip. So let's start the clock as soon as the molecule hits this wall right here. How much time will it take to hit the other wall? Well, it's going to cover some distance, L. That's the distance between the two walls, and divided by its velocity, which is the distance in time that it travels. So when you do that division, that's going to equal a time. So that's the time it takes to go from the far right wall to the other wall. The time that it takes to come back is going to be twice that. So 2 times L over the velocity x is the time to return to the right wall. Okay? So if that's the time, well then what's the frequency? That's the inverse of the time for something to happen. So that's going to be this here. Okay? Now we can go back to the units of this, remember, are time inverse. Now we can go back to what I said earlier about force. And force is going to be that the absorbing of the momentum by the wall. So that's going to be 2m vx times the frequency, which is inverse time. So I get this expression. Okay. In the case of n molecules, I did 5 vectors on the previous slide. Whatever number that is, you're just going to multiply that number of molecules times this value for the force, and this is the total force absorbed by the wall. Okay. Now the pressure absorbed by the wall is simply going to be the force divided by the area. And we just calculated a value for force. That was N mvx squared over L. And let's just say the area of the wall is L squared. Now I have mvx squared over V. And I could rewrite PV equals NMVX squared. That's equation 2.2. Now, there's a lot of assumptions here. The assumption is in this equation that this pressure due to collisions with the right-hand wall is all due to a bunch of molecules that are moving at exactly the same velocity. Of course we know that's not true, really in two senses, because when you have a sample of gas, not every molecule has the same overall velocity, and also, since these molecules can be bouncing all over the place, very few of them are going to be pointed right at the wall, which is why we have to substitute with a distribution. I'll say eventually. I'll worry about that a little bit later. But the other thing is that expressing a collision based on just the x component of the velocity, it would be absolutely impossible to get any kind of measurement of each and every molecule's x component of their velocity, which is where averages come in. So we would like to replace Vx with a mean. If there's some way to get that, that would be wonderful. But guess what? There actually is. Going back a few slides to the very beginning, when we talked about the overall velocity vector, turns out that it can be shown that taking the average velocity vector can be written this way. And so with a substitution, as we did before, we're going to rewrite 2.2 as P equals N mv bar squared over 3v. I mentioned this in class. This is because all of these guys are equal to each other. Any one of them is going to be 1/3 of the rest. All right, so our pressure expression that connects the pressure to the mean velocity does a clever little just multiplication of 2 over 2. What does that do for us? Well, does this look familiar? 1/2 mv squared. And I hope it does, because that's going to be able to express the average translational energy of your sample of molecules and connecting it to pressure. Now we know that PV equals nRT. I'm going to substitute in the number of molecules over Avogadro's number for moles, and we get something interesting here. I'm going to rearrange pressure by itself and get nRT. Again, capital N is number of molecules over Avogadro's number times the volume. And then I'm going to compare these two and see if anything interesting comes out. And in fact, I get 2/3 times the average translational energy is equal to RT over NA. Basically, the number density canceled out. And so I can have an expression for the average translational energy is equal to 3RT over 2NA, or 3/2 kBT if I define this thing called the Boltzmann constant as the gas constant divided by Avogadro's number, and that's 2.6. So thus ends our derivation that connects translational energy to temperature of molecules. You could pick up right where this ends and go into page 39 and then sort of lay on top of it all of those expressions for the distributions. Because, of course, writing something like the average translational energy can have many contributions in a large sample of gas. So being able to write an expression for the entire collection is really important. So I hope this helps at least a little bit. I'll set up some times this week that you can come by to ask specific questions, but we should be ready to move on to complete Chapter 2 on Monday, and then go right into Chapter 3 and begin to talk about energy in a more explicit way. All right, take it easy. I hope this helped. Bye.